So the teacher says to the student, what is 11Q minus Q? And the student says 10Q. And the teacher says, you're welcome. Hey, it is time to start 11.3. We're going to talk about probabilities of multiple events today, beginning with a rule that we'd like to call the addition rule. To get us started, I put together a couple critical thinking questions, and I would love for you to take your own look at 1, 2, and 3. They're taking the questions from the previous lesson a step further, and I want to see what you could come up with before we go over them together. So pause the video, give 1, 2, and 3 a try. Come on back, and then let's take a look at number 1. We've seen questions. We were just introduced them the other day. Ones, where should I go here? Ones that had you roll 2 dice, right? Or number cubes, as the book sometimes calls them. So your outcomes are the numbers 1 through 6 on either die. And we made a table in the previous lesson, but generally the table has to do with sums. Well, here they're talking about differences. So when I construct this table with the numbers 1 through 6 for the first die and the numbers 1 through 6 for the second die, I'm going to subtract the two values instead of adding. So 1 minus 1 gives me 0. I'm going to put the differences here. 2 minus 1 gives me 1. So I'm subtracting the numbers in those column and row and putting them down here in red. 3 minus 1 gives me 2. We're talking about the positive difference. I know 1 minus 4 is negative 3, but I want the absolute value of the difference in this table. So this is 4 minus 1, 5 minus 1, and 6 minus 1. Definitely start to see a pattern. 2 minus 1, 3 minus 1, 4 minus 1, 5 minus 1, 6 minus 1. So the pattern starts to come up. Now let's continue it, right? We're going to take 2 and subtract 2 to get 0 there. 3 minus 2 is 1. 4 minus 2 is 2. 5 minus 2 is 3. 6 minus 2 is 4. So we get 0, 1, 2, 3, 4 down that column and row. Continuing with the differences, next up is 3 minus 3. So it looks like I'm going to get a diagonal of zeros running down here. So 1, 2, 3, and 1, 2, 3 for those differences. So you keep the pattern going. 4 minus 4, so 0, 1, 2, 0. Oops, I already have the 0, so make that a 1 and a 2. And then lastly, we've got 5 minus 5 is 0, 6 minus 5 is 1, a 1, and a 0 down there. Okay. So now the table is constructed. That was the time-consuming part. It says, what's the probability? You roll the 2 dice, and the difference between the two numbers, is that a heart? Does that mean we love math? No, it's just less than 3. I guess it's a little bit less romantic than that. So less than 3, we got to count them up. Most of them, what you're leaving out are the ones greater than 3, just those 4s and those 5s out there. So, and actually the 3s as well. So less than 3 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, should be 24 outcomes out of those 36 total. You still, by counting principles, have 6 options for the first die, 6 options for the second die, giving you 36 total outcomes. And you can reduce that to say the probability is going to be 2/3. So just another way to think about a 2 dice problem. Taking a look at number 2, it says you have this school that has grades 1 through 6, and all of these grades have an equal number of students, but grade 1 is twice as big. Now, it doesn't tell us how many students are in each grade, but we probably still should be able to find this probability. So maybe since I don't know how many are in each grade, sometimes in algebra, we'll just call that x, right? We'll say let x equal the number of students in, let's say, each of those grades. So in grades 2 to 6, right? Each grade 2 to 6. That would mean how many students, number of students, are in grade 1? In grade 1 is going to be double that, so 2x. I bet this could give us the total, right? Because we need number of kids in grade 3 divided by the total number of kids in the school. If I add up, this is 5 grades. I add up 5 of these plus 2 more, so 5x for all the kids in the other grades plus first grade gives me 7x total students in the school. That's going to be my denominator. In the numerator, P of grade 3, I want to put the number of students, the quantity that's in grade 3, and that should just, we called that grade 3 was just x, right? Grade 3. So that is, those x's can cancel. We can reduce this, and you have a 1 in 7 chance of picking a grade 3 student. Now, you might be able to do this problem just by looking at it too. You don't really have to create an algebraic expression, but it's another way to think about it, that you're doubling the kids in grade 1. All right, so we've seen coin problems before. Now we're tossing 3 coins. You're finding the probability that all 3 faces are the same. I want to star this one. So for 3 coins, I wonder, we probably need total number of outcomes, and we want to see what we're talking about, which outcomes we care about. Can I do a blank? Let's use counting principles for the 3 coins. A blank for the number of outcomes for each coin. So 2 outcomes for the first coin, heads or tails, times 2 outcomes for the second coin, heads or tails, times 2 outcomes for the third coin, heads or tails. There are 2 to the third, or 8 total outcomes. That'll be good for your denominator of this experiment. Now we got to talk about what cases we care about. Probability that all 3 faces are the same. How many cases is that? Well, one of them, I'll say this is the probability, is that you get heads all 3 times. So heads, heads, heads. The other probability is that you get tails, 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 right? Either of these, I'll say, or tails, tails, tails. That is 2 possible outcomes out of the 8 total that we had calculated. So a 1 in 4 chance that you'll get heads, 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 or tails, tails, tails. We will come back to examples like this. 4 leads us right into our lesson for today, because today is about the word or, and we kind of use the word or in the last question as well, but we'll do something with adding here. Here's your experiment. You're flipping a coin and you're rolling a die, right? So we'll say the sample space we know is a list of the total possible outcomes. I'll put it in curly brackets. Use the coin first. So the coin could land heads and you can get a 1. The coin could land heads and you get a 2 all the way through 6. So heads in 3, heads in 4, heads in 5, heads in 6. Or the coin could also land tails and you can get each of those 6 numbers. So tails in 1, tails in 2, 3, 4, 5, and 6. We should have been able to guess that there would be, count them, 12 total outcomes, because if we said the 2 outcomes for the coin times the 6 outcomes for the die, 12 should be the answer. That should be a denominator for some of these probability expressions. But now we've got them all listed out, and we'll see if that'll help us to answer B, C, and D. Probability you get a 2, not just a 2 or a 6. Well, there's 2 outcomes that have 2's in them, and there's 2 more outcomes that have 6 in them. You are adding up all those total outcomes to get 4 outcomes out of 12. That's a 1 in 3 chance. Heads or 1. Okay, so heads, that's half the outcomes. That's 6 of the 12. Or a 1, this is the one we left out, that outcome there, the tails and 1 would also work for this. So I'm going to add those total outcomes and get 7 total. All these 6 with heads and then the tails and the 1. 7 12s actually does not reduce. And if we're writing things down, that's Miss Wesley's birthday, July 12th. I always like it when 7 12ths comes up. Tails or an even number. Well, tails is this entire bottom row, all 6 of those outcomes out of 12. Plus the evens that we left out from the top row. So heads in 2, heads in 4, heads in 6, those 3 even outcomes would also work for this. So I'm looking at a 9 12ths for this one. We could reduce and make it 3/4 of the time. Nice job on the critical thinking. Stay tuned for the next part.